This is a short video that I'm recording to summarise the work that I published along with a colleague of mine, Jack Townsend, and collaborator Tim Tudor in the Royal Aeronautical Society's Journal back in 2016. In this work we were trying to optimise the design of the rear wheel fairing that wraps round the external rear wheels of the Bloodhound supersonic car land speed record vehicle. So the problem statement that we started off with was basically, given that the main body of the Bloodhound vehicle had been fixed, and in fact at the point of doing this work was already in construction, we were then set the task of trying to find an optimum design for the fairing that wraps around the rear wheel of the car, which you can see in the lower figure here is the red part wrapping around that rear wheel on a parametric model that was used for this study. So the first part of the project was really to find a sensible parameterization of the space and a simplification of the geometry to allow us quick turnaround times of the CFD aerodynamic simulation model. To do this, we blocked off the intakes of the car, got rid of some of the features that we didn't think were important in this study, like the presence of the front wheels and the fin, and we chopped the car down the middle, down the symmetry plane, again just to try and reduce the computational time of running CFD simulations so that we could turn around as many CFD simulations as possible. We then looked at a sensible parameterization of this rear wheel fairing shape. We decided that the central section of the fairing would actually be fixed, and we refer to this in the paper as the static central hub. And then 6 parameters were used to define the essentially the positions of the leading and trailing spikes that form the fairing geometry. The first check that we did was to make sure that this parameterized, simplified model of the car and the fairing still produced sensible aerodynamic performance in comparison with the full fidelity CFD model, that we were capturing a sufficient resolution of the physics to be able to assume that any improvements to the design of the parametric model would translate back to a full fidelity model. And following this, we then explored, ahead of the optimization study, a comparison of running with an open fairing and a closed fairing. So that is, the open fairing was a slightly smaller in terms of frontal area fairing, but had the top of the wheel actually exposed to the airflow. So even though this fairing had a lower or smaller frontal area, it turned out that because of that exposed wheel rotating into the airflow, the drag coefficient of the open fairing was lower than higher than the closed fairing. So the closed fairing was used as the baseline for the remainder of the optimization study. In the paper we look at the output for various objective functions. The main one I'll talk about in this video is optimizing for simply drag minimization, taking no other things into consideration. But we also considered an optimum fairing design for drag and lift minimization, where an alpha parameter was used to determine to what extent lift minimization drives the optimization process, and a lift constrained drag optimization case where we were trying to minimize drag whilst also minimizing the variation or the change in lift from the baseline lift that was being generated by the vehicle. We sampled the 6-dimensional design space using 60 design points, which was computationally about as much as we could fit into the time frame we had for the project, using Latin hypercube sampling and then a response surface fitting technique to try and get a feel for the input parameter responses, so how those design parameters phi1 to phi6 ultimately drive the output objective function, in this case here drag coefficient. Having done this, it became quickly clear that this kind of quite simple design of experiments, response surface approach to doing the optimization wasn't going to be sufficiently trustworthy because the error bars on those response surfaces were too large. So we moved on to use a Nelder-Mead optimization procedure based on radial basis function interpolation of the design space from those 60 samples, and got responses like this. So in this case, this is the result that's shown in the paper for simply drag minimization. So starting with this baseline fairing design which had a drag coefficient of about 1.04. The optimizer managed to reduce the drag on the fairing down to under 0.98, which is a 6% reduction, which in terms of overall car performance is significant, because a third of the overall drag of the car at high speed comes from the rear wheel fairings, or the rear wheel and suspension system. For more details, obviously refer to the paper published back in June 2016 in the Royal Aeronautical Journal.